today we'll talk about motion and how to measure it. So basically what we want to know is to know if we are moving or not. So let's start from an example. Let's consider that we are inside a train and that we have no windows, no external references, or no external information, like GPS or tower control information. Now we want to know if we are moving or not. And if we know that we are moving, we want to know if we are changing our orientation in the space. Okay? Again, without external information. And how to do this? Let's build some bases. So I have talked about motion. Let's start from the Newton laws of motion. We know that from the first law, an object will not change its uniform motion unless a force acts on it. Uniform motion means constant velocity on a straight line. From the second one, we know that we don't have uniform motion only if we have external forces. And acceleration has to respect this law. So it's proportional to the mass and to the external forces. And let's consider a realistic example to see how this works. So let's consider a man inside a box on a skateboard holding a spring. So something we experience every day. We know that from the first law of motion, we cannot tell the difference between no motion and constant motion. So for this case, without external information, we cannot know it. But let's consider other cases. If we apply a force to the box, we have that. Due to the second law of motion, we have an external force. The box wants to move, so change its velocity. This guy is on a skateboard, so there is no friction and no force applied on him. So due to the first law of motion, we don't want to move. So there is a relative motion between the two. And we see it in the change of length of the spring. So this is something that we can measure, we can see, and we want now to know if we can quantify this. To do this, let's simplify the problem. As absolute observers, what we see is that the box is moving, what is inside is fixed. So from the point of view of us, the box is moving, the guy is fixed. But from the point of view of the things that are inside the box is fixed and the thing is moving. So from the point of view, this guy is the one moving towards the box. And we know from Newton's law that we have a motion only if we have an external force. This is not a real motion because in reality this is fixed, the box is moving. But in this new reference system, we want to use Newtonian mechanics. So let's say this is moving, we say that there is an apparent force acting on this. And the apparent force is equal to the mass times the acceleration, because we want to use the Newtonian mechanics. The other force that we have is the force inside the spring due to the relative motion. There are the only two forces inside, they have to be equilibrated. So from this relationship, we can compute acceleration. So we cannot compute uniform motions, but if we have the accelerations, we can compute them. We need to know the stiffness of the spring, but if you choose it, we can know it. We need to know the mass. It's a parameter that we choose. The problem is that we need to measure the displacement. If we can measure the displacement, we can compute accelerations. How we can do this? Let's introduce another concept. We know that metals are electrically neutral, so the same amount of positive and negative charges. If we try to push extra charges, we can. No matter how strong is the force, they will always be repelled by the positive charges. But if we consider a different condition in which we have two different plates, they are both electrically neutral, but if we try to push extra charges on the first one, we can have extra charges. These charges will repel the same amount of charges on the second plate. So at the end, inside the plates, we have the same amount of charges. But with the fact that this plate is now negatively charged, because there are more negative charges than positive ones, and this one is positively charged. So first effect of having two plates, we have two different charges, opposite, so there will be an attractive force between these two. The second effect is that we have an outflow of current. And this is what we call a capacitor. So if we have two parallel plates, we apply a voltage at the first one, we have an outflow of the current at the second one, and we will have an attractive force between these two. This outflow of current is something that we can measure, but it is not easy to deal with current, so we introduce the concept of capacitance, which is simply the amount of charges that we can store at the given voltage. And this depends only on the geometry. It's equal to the permittivity constant times the overlapping area, because greater areas means more space to store more charges, divided by the distance between the plates, because if we have small distances, we have greater electrostatic forces. How this would help in our case? Let's consider this configuration in which we have 3 plates. These 2 are fixed, this one can move. If we apply a voltage to this one, there will be a capacitance between these 2. So there will be an attractive force between these 2 plates. And this is the value of the force. If we apply a voltage to this plate, there will be an attractive force between these 2. And by controlling the voltages of the 2 plates, we can control the motion of this plate. So we can use this configuration to impose a motion, so to move something, or if this thing is moving for other reasons, for example, if it's attached to something that is vibrating, we can measure the capacitance at these plates because they depend on the distance between the plates. So we'll have the capacitance is the area divided the distance, but the distance changes with the displacement. So if we measure the capacitance, we can compute the displacement. But this is a nonlinear relationship, and we don't like it. We will prefer to have a linear relationship. So let's consider a different shape. In this case, we call this a cone finger, but basically we have just horizontal plates instead of vertical ones. So we have a capacitance between this one and this one, this one and this one. But in this case, during the motion, as you can see, the distance between the plates didn't change. What changes is the overlapping area. But the overlapping area appears at the numerator. So in this configuration, during the motion, the capacitance changes linearly with the displacement, while the force did not depend on the displacement, but just on the applied voltage. Okay? So we can use this configuration to apply forces to something or to measure displacement with a linear relationship. So now we can measure displacements. So let's return to our initial case. We have a rigid box. We attach a moving mass with a certain stiffness. And now, if we attach a cone finger system, we can measure the relative displacement between the mass and the box. This is something that we can measure. If we measure this one, it depends linearly on the displacement. We can compute the displacements. Once we have the displacements, we can compute the acceleration. So with this configuration, we can compute accelerations. Okay? So now let's build something that can do this stuff. So let's start from a piece of silicon. So we need a metal. And on top of this piece of silicon, we put a protective material just in some regions. And now, with a chemical process, we can eliminate all the unprotected areas. So we remain with just the shape that we protected at the beginning. Now, if we attach this thing on a PCB, and if there are external accelerations, this device will start moving. And by moving, we have these cone fingers. We will change the displacement. We measure the capacitance variation, and so we can measure the acceleration. So this one is what we call a MEMS, so microelectromechanical systems, because this is in the dimension of micrometers. It's a mechanical because it's a moving system, electrical because we measure electric quantities, the capacitance. And with this system, we can measure accelerations in the x direction. What about y and z? For the y direction, we can simply rotate this 90 degrees, and we can measure the y displacement. For z displacement, we can try to rotate this in the out-of-plane direction, but this is something that we can do, because usually we have limits in the thickness, and we cannot assess perfect verticality. So we actually need something with the mass, central mass that moves in the out-of-plane, so up and down. But out-of-plane motions are difficult to detect, and because with these cone fingers, so with cone fingers in the plane, are very simple, clean, and easy, and they give a linear system, a linear reading. So we want to use this also for out-of-plane motion. How we can do this? Let's start from improving our fabrication process. So a piece of silicon, we protect some areas, we delete all the remaining areas, and then we attach a second layer of silicon. We protect different areas, and we eliminate the remaining areas. So this is a double layer system. This is overly simplified, what we call the double thermal process. It was developed by ST Microelectronics. It's a company that produces MEMS, in which we have two different layers, and we can control both of them. And what we have here is a long beam with an S-shaped section. This is a non-symmetric section with respect to the vertical axis. Why do we need this? Because with symmetric sections, like this one, we have that the vertical direction is an axis or is a principal axis. So if you push with a vertical force, you will have a vertical displacement only. You push with an horizontal force, you have horizontal displacements only. With non-symmetric sections, we have that the principal axis is not the vertical one. So if you push with a vertical force, you have a vertical and horizontal displacement. So basically, you push this vertically, it will move diagonally. So we have a coupling between two displacements, and we can use this as a coupling mechanism. This is the real beam fabricated with the real limits of the process. It seems more complicated, but the physics is the same. You have an S-shaped section. And we use this to design this, which is basically a big central rectangle. So it's a mass moving in the out-of-plane direction. And we have these two additional frames, lateral frames, that are moving in the plane, so just in the y direction. We connect these two with this beam. So we couple these two movements. When the mass moves in the out-of-plane, we have that those frames move in the plane. So we can measure the displacement, not of the mass directly, but of these frames, with the advantage that this is in plane, so we can use the comb fingers that we saw before. And this device was actually fabricated. This is a SEM image, and as you can see from this zoom, we have two layers. This is the bottom layer, this is top layer. We have other regions in which we have just one continuous layer. And this was fabricated and tested. These were the results, where in the x-axis we have the acceleration, so the things that we want to measure. In the y-axis we have the capacitance, the thing that we measure, and there is a linear relationship between the two. So we like this. And this is one of the first examples of linear reading of out-of-plane movement of the mass. So this design actually worked, and when a MEMS works, it's very strange, but in this case worked. So let's hope the best. And so to answer to the first question, yes, we can compute motion without external information, just if we have non-uniform motion. So if you have accelerations. And we have these three devices. These in X and Y, something you find in literature, we introduce these things. So the novelty is that with this design, we can measure also Z accelerations with in-plane movement, so in-plane reading. Okay, what about the orientation now? This is more interesting. So let's again consider what happens from the point of view of an observer in this simple example. Pay attention to the red dot. This is moving along a straight line. So it's a straight line, a uniform motion, while the external frame is rotating. So it's changing its orientation. So this is a straight line, uniform motion. But in the point of view of the relative system, this is what we will see. It's curving, so it's changing its direction. It's not a real changing in direction because it's a straight line. This is just a relative observer. But again, we want to use Newtonian mechanics, so we say it's changing direction. It means that we have a force perpendicular to the displacement. So we can compute this, and we find the expression of the force that we call Coriolis force. It's a mass times an acceleration. But in this case, we don't have an acceleration, a direct acceleration. It's omega vector v, where omega is the angular velocity of the rotating frame, while v is the linear velocity of this red dot. Okay? So we have Coriolis force just when we have a rotating frame and when we have a moving object inside of it. If we have no motion inside, we will not have the Coriolis force. Okay? So we said Coriolis force acts on a rotating object, and it's always perpendicular to the velocity. So let's try to build something that we can use to detect this. So again, we have a rigid box, we put inside a mass, but now we need to constrain it also in the other direction. We need a 2 degrees of freedom system, and we impose a velocity on the horizontal direction. So this is something that we choose, we impose. How to do this? Remember, we said that with com fingers we can measure displacement or input forces. So we can use some com fingers to input forces to give a motion. So while this is moving, if we have a rotation of the frame, we will experience a Coriolis force in the perpendicular direction. So basically this is what happens. This system is moving along the horizontal direction when omega is 0. When we have a rotation of the frame, this will experience a vertical force and we will have an elliptic shape. If we can measure the displacement in this vertical direction, we can compute the Coriolis force, and then we can compute omega. Okay? So let's build another MEMS that can do this stuff. So let's start from an horizontal mass. This is a rectangular mass constrained to these points by means of horizontal beams. This can move just in vertical direction only. Let's put other two masses that can move just in horizontal direction. And now we need to connect these two with an intermediate system, and this one is connected to both of them and can move in both directions. Okay? Don't worry if you can see it. This is what will happen. So this is the system. Inside of these two lateral frames, we have the com fingers that provide the force. So this will start oscillating, and this is a movement that we control when we have omega equal to 0. As soon as we have a rotation of the frame, this will experience a Coriolis force in the vertical direction. So this will start, so this square ring will start to move in an elliptic shape, and this internal frame will start to move just in the vertical direction, okay? So when we have no rotation, this is fixed, it's not moving. When we have rotation, this is moving in vertical direction. So we compute the displacement of this one, we can compute the rotation of the frame. And this is to show how this quantity, in this expression, we have a vector product, which means that these three quantities are perpendicular to each other. So we have the Coriolis force, the motion that we impose, and the axis around which the system is rotating. Okay? So if we want to compute the rotation around the z-axis, we need to have both the sensing and the driving motion in the plane. So the mass has to move along x and y. And this is what we call a yaw gyroscope. So we're measuring the rotation around the z-axis. But if we want to measure the rotations around the y or x-axis, we need to have the drive or the sense in the out-of-plane direction. So we need the mass to move also in the out-of-plane direction. But again, we don't like out-of-plane movements because they are non-linear and difficult to control. And we want to control everything in the plane. So we can use the same concept, we can extend the same concept that we saw for the accelerometer. So let's build another MEMS. This is the last one, I promise. We have, let's take these two frames, the light blue frames, that can move just in the horizontal direction. Now we have this central mass that we want to move in the z direction. And first we need to connect it to those frames because it cannot float. So we connect this, and these elements are designed such a way to allow z displacement. And now the light blue ones have to move along x. The mass has to move along y, along z. How we can do this? We want to move something in the plane. So we put two additional frames, and these ones can move just along y, so just in the vertical direction. And between this one and the mass, we put an intermediate frame. And you cannot see this, but inside this red frame, we have those S-shaped springs that we saw before. So this red element acts like a motion conversion system. And this is the device during its motion. So we are controlling this frame and this one, so it's a movement in the plane. We have this element that acts like a motion conversion, and the mass moves in the out-of-plane direction. You see these two frames are not moving when omega is equal to 0. When we have a rotation around the y-axis, the mass starts moving in an elliptical shape, this time in the plane x, z. And these two frames starts moving. So the same concept of the first gyroscope, it's just a little bit more complicated because we have an out-of-plane motion, but these two frames don't move with omega equal to 0. This moves when omega is different from 0. We measure the displacement of these ones, and we can compute omega, okay? And so now we have everything. Again, we can measure the angular rotation in all the directions. And the novelty is that for the first time we have a pitch and roll gyroscope with full in-plane motion. So we have the driving frames and the sensing frames, so the one we move and the one that moves just when we have a rotation, fully in plane. So again, we have a linear signal, and it's easier to control things in the plane than in the out of plane. Okay, so to conclude, the first question was where we can measure displacement, we can measure motion. Yes, just if it's not uniform, so just accelerations. What we introduced, so the novelty is that for the first time we have an in-plane reading of an out-of-plane motion. The second question was, can we measure the change in orientation? Yes, but we cannot measure with this device, we cannot measure the angle of changing. So if we are on a certain angle, we rotate 90 degrees, we cannot measure 90 degrees with this one, we measure the velocity of rotation. So if we know the velocity of rotation and we know the time in which it acts, we just integrate and we have the rotation. And the novelty is that in this device we have full in-plane pitch and roll gyroscope, so driving and sensing in the plane. The disadvantage of these new designs are that we have more complicated geometries than traditional sensors because we have these Boshoff conversion elements. We have a more complex fabrication process because we have 2 layers instead of 1, which means more constraints during the design. And the last aspect is that the motion conversion system is very stiff. And stiff elements means that we need larger forces to have the same displacement, so more energy consumption. But at the end, we are pretty happy. We have one MEMS that works, and it's still strange, and we have one MEMS that we need to produce. And the spoiler is that this won't work. And thank you. So these are the people to blame. Thank you.
Thank you for the compact and clear presentation. Now it's time for questions. Anybody here? We have some experts.
I know that gyroscopes are quite for pattern. So it could be really assessing the location. If they're not as good as it. How do you compare this design that is out there? And you can give us some from that. I'm interested in that.
Can you repeat the question?
So, given that gyroscopes, MEMS gyroscopes, are not escapable to detect rotation as there are other methods, and they don't use them in verification very strongly as I know.
Yes, unfortunately not, because we are the people that work in UNI.
Yeah, okay.
So you point another country and you bomb your own country. They will install our devices.
Exactly. So I wanted to ask you how your devices are this
Okay, yes, these devices that I show you cannot be used in that area because they are not that precise. But there is another kind of gyroscopes, and you will see this in one of the next PhD talks that can measure directly the angle instead of the angular rate. They are more complicated, but they are more sensitive. So I think that today there aren't MEMS precisely enough to be used as the mechanical ones, because we don't have just the MEMS gyroscopes, we also have mechanical gyroscopes, which you see in, for example, military planes, but are this big. MEMS are 1 millimeter long. Okay, so if you want to see them, you have to ask to the guy behind you because he's working on them. He's hiding, but he's the one working on them. Welcome.
Questions? There is some talk about applications and use of the devices. Could you sort of give us a picture of what are the fields where these devices have been developed for?
For the accelerometers have been developed a lot for the consuming market. So in smartphones, for example, to detect rotations, the change of rotations, you use them in safety devices like airbags. So the airbags are actuated by accelerometers because during an impact you measure a large acceleration. So you have a certain speed during the impact. You pass from, I don't know, 50 kilometers an hour to 0. So you detect this acceleration and you can actuate the airbag. And they are used gyroscopes with micro mirrors, which are different devices, have been used to real virtuality devices. So because when you put like the glasses, you change the orientations. So you need to measure the change of orientation, so to change the. And I think the two biggest markets are the consuming one and the automotive one. So for cars.
Show the calibration for linear motion. What is the range of accelerations?
It depends on the device. If you want very precise devices, you can reach 5G measurements. For more, let's say, less precise devices, you can reach 50, 70 Gs measurements.
Thank you.
You said that the
devices,
you said that the devices require higher forces and so consume more energy compared to the single one. Do you also have a constraint on the dimension in plane? Do they need to be larger, or can they still be just as small
the dimension is given by the company. So we have limits on the dimension depending on what they give us. So usually we work on dimensions like 1 millimeter per 2, or for larger applications you reach 3 millimeters per 3. But for more consuming devices, they are very small and you have 500 microns, so half a millimeter.
So, and just curiosity, because I'm looking out this topic. So, if you go back to your slide number 4, you basically have a small structure that behaves like an accelerometer, but actually what you can see is a small structure can be sheared by fluid, and therefore it can be used as a basically device to measure the shear force exerted by fluid on a surface. Something that is actually or is
not with this fabrication process, because these devices are not open or closed inside boxes, so they cannot communicate with the external world. So you cannot measure the flow of a fluid, not with this one at least.
But there is some type of sensor like this that allows us to measure the shear
I don't know, not in the field that I'm working on. But I'm not sure, because at this small scale, I think you will have a lot of, how to say, the surface tension of the fluid will play a very high role compared to the shear forces. So maybe, I don't know if you can use them. Welcome.
Well, you can do something. There are words in which you place on the surface drawing some pillars of more things, and these can indirectly activate the sense of the surface. Or you can also, with again, more to the surface, feel the local pressure and again with the rest of that. So there are or there are other techniques to measure the flow, and so you can design a flow meter.
So you talked about two questions. So in regards to the displacements and the geometry that you have, here it seems like your XY spacing is quite large compared to the size of the geometries, or
No, it's just amplified for the animation.
So the cones also amplified, or not?
The dimension of the cones? Yes, absolutely.
And so the out of plane displacement that you actually have is not so big that you basically you had some dimensions on the XY, but you didn't talk about the Z plane of your new sensor. So do you also have the requirements for your Z?
Yes, because we have, okay, you can move in the out of plane direction. In the top direction, you are free, but at the bottom, you have the PCB. So you have some layer, you cannot move, you cannot touch it.
And so for the sensors that move regarding to the Z direction, you're putting them higher or
No, we cannot control this dimension. So the thickness or the distance between the this layer and the MEMS is given by the fabrication process. So it's fixed. We design them to never touch the bottom, so the surface. So we need to control the displacement.
So that also limits you, I guess, in the acceleration or the rotation in these cases at the end that you're able to measure.
Yes, but not that much, because with small displacement we can measure quite large sensing signal. So we don't need very large displacement. Also for the gyroscopes, so with the other animations, for example, in this case, you see this motion, okay, it can be large, but this one, due to the Coriolis force, is 3 orders of magnitude slower than this one. So if you move like 1 micrometer in this direction you move 1 to 2 nanometers. So it was exaggerated just for the animation, but they're very small.
And then my second question was about these, the cones that you talked about right at the start. You say that there's a linear relation, that is quite obvious. However, what I imagine, at least when I look at the cones, is that the capacitors can also talk with the surface that is quite to the left and to the right of it. So they're not exactly, like, it's not exactly the same thing. So I'm imagining the law is more complicated than what you are giving you.
Maybe you're talking to the, okay, this is a cone. So this is the configuration. We have 2 plates with 1 plate in the middle. So in this case, we have that these charges, so we have a force between these two, and the same force between these two. So in the overlapping area, you have no effect.
And in the green area, there's nothing? So
in the green area, yes, you have these effects, but you have, this one and this one gives a net horizontal force, the same for this one, the same for these ones, but as you go far from the tip, the forces become lower and lower, because they decrease with the distance squared. So at the end, just a small portion near the tip of the cone really contributes to the force. So during the motion, as you can see, the green area never changes. So this is why the force is constant and the capacity is linear.
So it doesn't go all the way through. I mean, I'm guessing it's possible. So the green area should
No,
be always the same area.
we need to always maintain a certain distance between the tip and the end of the.
Very
yes.
Yes. So there are few elements in your design which are very flexible, while others are very stiff. Which is the design phase, the design procedure you adopt to find the, say, the final solution of your device? Are there specific criteria or?
No, with this, okay. Yes. We start from the movement that we want. So before starting to design this thing, we know that we want the central mass to move in the vertical direction, and we want this to move in the horizontal direction. So we constrain them. For example, this needs to be very rigid, because we need a perfectly rigid motion. We don't want deformation of the central mass. And these elements are flexible, because we need the motion in the vertical direction. The same for this one. As you can see, this beam is flexible in this direction, because we want this to move along X, but it's very stiff along Y direction, because this beam, when you move in the X direction, you activate the flexible stiffness. When you move in the Y direction, you activate the axial stiffness, which is more stiff. Okay? So the starting point is which are the movements that we want, and then we need to make them possible with some flexible parts. We use flexible elements because with MEMS we cannot use like mechanical movement. For example, we cannot have two surfaces in contact that move like this, and we can just rely on flexible elements. Was this a question?
Okay, that's an interesting question also on other domains, so the topic stimulated. I will thank you very much, and I think it's time to enjoy